Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process. If you would like to love others, first learn to love yourself. This is very important, as all of us, we always desire to have love and affection from others, therefore we love others, and for that we need to understand ourselves and also try to love ourselves. Before starting this lecture, let us recall what we learned in the last lecture. We basically looked at some of the performance parameters, defined them, and see how they can be used for assessing the various rocket engines. And most important performance parameter that we have discussed till now is the specific impulse. And specific impulse, we have also related the specific impulse to the thrust and also mass flow rate of the propellant, and of course we use the acceleration due to gravity at sea level. Beside this specific impulse, we also define several other types of specific impulse, namely mass specific impulse, density specific impulse, and volumetric specific impulse. And apart from that, we also define thrust coefficient and specific propellant consumption rates. And today we are going to discuss about thrust and weight ratio, or impulse to weight ratio, which is defined as the ratio of the total impulse to the weight of the entire vehicle, including the payload, as given below. That is, IWR is equal to I divided by W. This is your total impulse. And this is the total weight of the vehicle. So, keep in mind that this is basically, and this W is consists of all the masses related to propellant, structural, and payload mass. So, I can say that this is equal to I can write down in terms of ISP into mass of the propellant into G naught, or G simply, because I am using G basically. And this is weight. If you consider, this is MP plus MS plus ML. Keep in mind that MP is the propellant mass, MS is the structural mass, and ML is the payload mass, into the G. So, this is cancel it out. So, you will get IW R, that is the specific heat ratio, is basically specific impulse into mass of the propellant divided by the mass of propellant plus structural mass plus payload mass. Keep in mind that these we call it as basically inert mass, or sometimes we call also the burn out mass. This is burn out mass. And if I can divide this by the MP, like if I divide it by MP here and MP here, I will get ISP divided by 1 plus MB by MP. Keep in mind that if I want to have a higher IWR, then naturally what you will have to do, you will have to reduce this term, right, MB by MP. Either I will reduce MB, can be, that means the burned out mass or the inert mass would reduce, or I will have to increase the propellant mass for a particular specific impulse, I can increase the impulse to weight ratio by either decreasing the burnt out mass and or increasing the propellant mass, or both combinations. Keep in mind that payload is generally fixed for a particular design, unless otherwise you can't manage, but structural mass is the thing what one has to decrease. And this can be also related to the thrust weight ratio. Keep in mind that total thrust weight to ratio dictate the acceleration of the vehicle, because of fact that thrust will be higher as compared to the weight, the vehicle definitely will accelerate, particularly when you are having higher thrust as compared to the weight. So, generally it is desirable to have higher thrust to weight ratio for a particular engine, or in other words the impulse to weight ratio should be higher, which is a part of the design. And for a constant thrust, maximum acceleration can occur just before the burnt out, as the vehicle mass is reduced due to consumption of propellant mass. Keep in mind that vehicle mass is basically changes as the propellant gets consumed, and at the burn out generally all the propellant mass being consumed. Of course, there might be a small amount of residual mass which will be remaining, which cannot be really consumed. So, except that most of the mass, therefore, most of the mass will be consumed at the burned out. Therefore, it is expected to have the maximum acceleration being occurred at the burned out. So, either the impulse to weight ratio or thrust to weight ratio is considered for comparing various rocket engines, so that we can say which design is good or which one is better, kind of thing, and how we can select certain engine for a certain application, particularly for higher accelerating vehicle like missiles and other things. We need to choose the higher thrust to weight ratio engine. And note that generally chemical rocket engine has higher thrust to weight ratio as compared to non-chemical rocket engines, and some of the data I will be discussing at the end of this lectures, toward the end of this lectures, and we can see that. And let us now define another ratio which is known as mass ratio. It is considered as the ratio between the burnout mass to the total initial mass, as given below, that is mr is equal to mb. I have already told you this is burn out mass, and this is your total mass, that is consists of m is equal to basically mr is equal to mp plus ms plus ml, and sometimes I will be using also, instead of mi, sometimes I will be using m naught as well. And keep in mind that this would be higher, so that you can have a better performance, and that means if we can achieve this higher mr by lowering the mb for a fixed value of mi. That means we will have to basically play with the structural mass. We can minimize the structural mass or reduce the structural mass, particular payload. So, that is an art which has to be kept in mind while designing a rocket engine. And let us take an example. A rocket engine with chamber pressure of 4.5 megapascals and nozzle diameter of 110 mm produces thrust of 17 kilonewton by consuming propellant flow rate of 7.5 kg per second with calorific value of 25 megajoule per kg. If the flight velocity happens to be 850 meter per second, determine the specific impulse, effective exhaust velocity, specific propellant consumption, thrust power and thrust coefficient. This example is taken just to illustrate how we can estimate this performance parameter this engine. Let us look at what are the things given in this problem. That is PC, chamber pressure is basically 4.5 megapascal. Megapascal means around something 45 atmospheric pressure, and the nozzle diameter dn, if you look at, is something 110 mm. So, and this is producing thrust of something 17 kilonewton. It's a very small force being produced by this engine, and it's consuming, the propellant mass is 7.5 kg per second, and calorific value of this propellant is SC is 25 megajoule per kg. The flight velocity with which this vehicle is moving is V is 850 meter per second, and we'll have to find out the specific impulse ISP and effective velocity V equivalent, exhaust velocity, and specific propellant consumption SPC, and thrust power, that is the thrust power PF, and thrust coefficient. So, what we will have to see that how we can obtain this. We know this ISP, we have already derived this expression in terms of thrust F by m dot P into G. So, F is given 17 kilonewton, that is 10 power to 3 into the 7.5 into 9.81. So, we are getting something around 231.06 second, and this unit is second, you keep in mind. That is the beauty of this specific impulse, that in all systems it is the same. So, now we will have to find out V equivalent, which is, we know that ISP is equal to V equivalent by G. So, therefore, I can write down ISP into G, that is 231.06 into 9.81. So, we will get something 2267 meter per second roughly. Of course, this is 6.7, but I am saying it is approximately that. Then we will have to find out specific propellant consumption. We know that specific propellant consumption is MP by definition the F, and which is equal to, very easily we know, because we know MP is 7.5 kg per second and F is 17 kilonewton. So, that is one way of finding out, but there is another way of finding out, that is, it is nothing but your V equivalent, right. We can find out, that is basically it is the MP by, I can also by directly I can calculate by that, that is 1 over V equivalent. So, that is equal to 1 over 2267 is equal to 0.0004 kg Newton second. So, that is basically for a 1 Newton force, you need to give something around maybe 0.4 gram per second kind of things. So, the thrust power PF can be determined by, that is PF F into V. That F we know it is basically 17 kilonewton into velocity is 850. There is a flight velocity. So, that happens to be something around 1450 kilowatt. Keep in mind that this is something you need to, it is producing a very high power, like is propulsive power is very much high, that is 14.45 megawatt. And the thrust coefficient is meant by CF. CF is F divided by PC A T, and this throat diameter is something around that is basically throat diameter AT. So, that happens to be the 17 into 10 power 3. PC we know that is something 4.5 megapascals into pi by 4 dn square. That will be happens to be something 0.72. So, you can see that it is a very low values, and you will have to take care of units, because if I have said in the Newton, this would be Pascal 10 power to 6, that you will have to, and also dn you can use as a substitute these values as a in meters, and you can find out this. So, now we will have to look at the energy balance of a typical rocket engines, because it is very important to know the energy balance, so that you can find out various losses and you can minimize the losses. For a typical rocket engine, the propellant energy what will be stored is being shown here, that is E initial, and that is equal to m dot p into delta H p. This is the rate of propellant energy. And then the combustion will be taking place thrust chambers, and not that all the fuel and oxidizer will be consumed in the process, and some residual propellant will be remaining, and that cannot be really converted into the combustion. Beside this, there might be some other things which will be losses will be there in the combustion, and that combustion losses is around maybe 2 to 3% of energy. That means the combustion efficiency we need to define, and keep in mind that this delta Hp is the heat of combustion of propellant, and the combustion efficiency I can define as the ratio of the rate of propellant energy released during the combustion. This is rate of propellant energy during combustion process. You see, is the rate of chemical energy release during combustion, and this of course we know the rate of propellant energy. This is basically rate of propellant energy or rate of energy contained in the propellant. So, this combustion efficiency, this may be something around 96 to 99% generally in a typical rocket engine one can think of, but however, if it is good, you can get even around 99% of that. So, beside this there will be heat losses in the combustion chamber, in the nozzle. So, therefore, there will be some losses, and then these losses will be something 1 to 3% of due to the heat being lost to the outside and other places. So, the total available energy here, the thermal energy which is available at the inlet of the nozzle is around something maybe 336 maybe percentage of the energy. So, therefore, this will be something 94 to 97% of energy which will be available, and lot of the thermal energy also will not be available converted into kinetic energy, and there will be some losses maybe something around 2 to 4% of the unavailable percentage of thermal energy will be unavailable for the being converted into kinetic energy. And the kinetic energy in the exhaust gas which will be going out without really converting into propulsive power. So, therefore, this thing will be around something around maybe 20 to 30 or maybe more like 20 to 40% kind of things which will be losses will be there, and the propulsive power if you look at it something around 40 to 50% one can get very with lot of difficulties kind of thing. So, therefore, we will have to define now a efficiency, the thermal efficiency, that is it is the ratio of kinetic energy available at the nozzle exit to the total rate of chemical energy due to propellant burning. So, if you look at a rocket engine, so this is your combustion chamber, and then it is going with certain velocities at the V exit, and the kinetic energy, this is your thrust chamber, and this is your CD nozzle. And at this point, let us say certain amount of energy which will be available, and then and it is moving at a let us say with a velocity v, and that is the flight velocities, and let us say a person is observing here kind of things, and then if you look at it is basically producing certain thrust power, that is PV, and then the amount of energy which will be kinetic energy which will be lost is basically m dot p into VE minus V whole square divided by 2, this is the kinetic. So, total kinetic energy available at the nozzle exit will be FB, that is the propulsive power, this is your propulsive power, and also this is the energy, kinetic energy, rate of kinetic energy leaving this is the observer, total amount of heat energy being released, and keeping in mind that we can be considering the combustion efficiency to be 100%. Let us now define another term which is called the propulsive efficiency. It is defined as a ratio of the thrust power to the rate of kinetic energy available at the nozzle exit. So, if you look at this is basically thrust power divided by the thrust power and the rate of change of kinetic energy. If you look at in the thermal efficiency, this denominator was the numerator, and this can be approximately equal to the MP into V, because the thrust F is nothing but MPV. Keep in mind that it has been assumed nozzle is fully expanded, and we are assuming that PE is equal to PA, and therefore, the F is nothing but your MP into VE. So, into A, and then of course, this is there. Now, if you simplify this and then also do that, we will get this m p into V e v divided by m p V e into V plus m p divided by 2 is V e square plus V square minus 2 V V e. So, if you look at this term, we will be cancel it out this, and if I divide it by this m p, so I will get basically is V e v divided by V e square V and 2, this is will be 2. So, if I divide it by this V e square, so I will get m p is equal to V by V e 1 plus V divided by V e whole square. So, this is basically an approximation, but it will go by that the propulsive efficiency is basically function of the flight velocity and exit velocity ratio. And if you can plot this propulsive efficiency versus this ratio of V by V e, you can see that the propulsive efficiency increases and it reaches something around 1 at when V e divided by V e is equal to 1, something like that. Of course, that is the beauty of this, that it is beyond this velocity ratio, the propulsive efficiency drop down, and in case of air breathing engines, you cannot really go beyond the flight velocity, which will be higher than the exit velocity, right. And that is the things, that means you can think of that is flight velocity is greater than the exit velocity can be achieved in the non-air breathing engine like rocket, because of fact that it is basically the ram drag is not there in the case of rocket engines, which is there in case of the air breathing engine, as it is injecting the air into its engine. That I have already discussed, that overall efficiency will be basically the ratio of the thrust power divided by the propellant energy rate which is consumed. So, if you look at, I can write down that in terms of two things. One is F b divided by F b plus m p V e minus V 2 whole square divided by 2 into the F b into m p V minus V square divided by 2. Keep in mind that this is nothing but your the propulsive efficiency and this is nothing but your thermal efficiency. Therefore, we can say that the overall efficiency is nothing but your propulsive efficiency into the thermal efficiency. So, that means if I know one of two of them, I can find out other one. So, generally in rocket engines, that overall efficiency can found out very easily. So, also propulsive efficiency and thermal efficiency can be obtained by knowing the other two. So, let us now look at the typical performance parameter of a rocket engine, that is we are considering the three chemical rocket engine. One is solid, liquid and hybrid, and this is your chemical rocket engine, and this is non-chemical. You can see that solid propellant rocket engine operates on 15,000 Kelvin, liquid is something 2000 3500 Kelvin, and of course, hybrid is in similar range. ISP is the lowest in case of solid propellant, and this is little bit higher in liquid, that is 300 to 460, and hybrid is little bit more. But you can see this, the thrust to weight ratio in case of solid propellant rocket engine is something 10 power to minus 2 to 75. Of course, for liquid, and for hybrid it is little higher or highest. And specific powers, that is basically it's expressed in kilowatt by kg, and it is kinetic energy power per unit exhaust mass flow rate, that is being assumed. And you can see that it is something for solid it is 10 power to minus 1 to 10 by 2, and whereas for liquid and hybrid it is very little bit higher than the solid. That is indicates that for kg of like amount of power produced per kg of the propellant is higher in this case, and this can be fly for maybe few seconds to few minutes depending on the design. Whereas the solar, if you look at this operates in the little lower temperature and the ISP is bit higher, but this is the thrust to weight ratio is very low as compared to solid propellant, and so also the specific power, because the engine is little heavier. Of course, one can propel it for a longer period, altogether can move for days together. And whereas the nuclear, the temperature 3000 and ISP is much higher as compared to the chemical rocket engine, and whereas electrical arc engines is something temperature is 20,000 Kelvin, and the ISP is much higher, order of something 2000 seconds you can get. But the you can see that this is the thrust to weight ratio is very low, and so also the specific power, particularly electrical arc engines, of course one can operate for days together. So therefore, this kind of non-chemical rocket engines are not really preferred for the operation wherever this earth gravitational pull is concerned. Therefore, the chemical rocket engines have a lower ISP, lower engine weight, and a very high thrust capability and higher acceleration. As I told, the thrust will be higher as compared to where the acceleration will be there, and high specific power as compared to the non-chemical rocket. So it is used profusely for all application, including the space. But however, due to the heavier engine and lower thrust capability and lower acceleration, lower specific powers, of course it may have higher ISP, but it is application is restricted to the what you call space applications. So therefore, we will be mostly discussing about chemical rocket engines. So with this I will conclude, and then in the next lecture we will be discussing about the rocket engine nozzle, and thank you very much.